Okay, so what I'd like to do is I'd like to go back over now analysis of variance and correlation and regression, right? So let's start with analysis of variance. And, matter of fact, now that I have it open, I'm going to open up a reduced data set from the Community Health Survey. Okay, this data set has stuff that's relevant to flu vaccination. Okay, as soon as it opens up, we'll take a look at what fields are in there. See if we get started.
How do we follow along with
If you want, I don't know. I think this data set is in the project folder. Is in the tab that has exam 3 and project, and inside of there it has the SPSS file. Okay, so I just opened it up. I'm going to go to the variable view so we can see what's in here. Okay, this is the same thing as the data set we looked at before, except that I've taken all but 10 rows. I took 193 rows and deleted them. So the only thing that's left is the stuff I want to work with. The other stuff, since I'm not going to use it, is just clutter anyway. I don't need it, right? So for instance, what's your age? I have something that's a numerical variable. And if you look over here, there's a little scale over here under measure. So SPSS knows now that that's a numerical variable. What borough do you live in? Well, let's see. I live in, well, the values are not in here, are they? Right? It doesn't say what the values stand for. So I have to go to the code book. Oh, you see, you've been working with this, right? Okay, I'm going to do this here. I'm going to look it up for myself. Do you remember all of them?
I know 3 is Manhattan.
Okay, hang on a second. I'll get to them. There we go, borough. 1 is Bronx, 2 is Brooklyn, 3 is Manhattan. 1 is equal to the Bronx. 2 is equal to, what was it again? What was it again? It was Brooklyn.
Yeah, you have the right one. You have to go to variables.
3 is Manhattan. 4 is Queens. I'm going to add that for Queens is 4. And 5 is Staten Island. I'll use the old name for Staten Island, Richmond. Right, that's the actual county name. It's Richmond. Okay, I'll click OK. So now SPSS knows what those numbers represent. In fact, if I go to the data view, you can see that instead of a number, there's the borough name there instead. Okay, now when you go home, this is going to be on. I'm going to upload this. You'll be able to see me do it, so you'll be able to step through it a little bit more easily. You don't have to worry about keeping up with me right now, because you'll be able to see what I did here later on. So Demog 1 represents the person's age, and borough represents a categorical variable, which is the borough that person lives in. So let's think about this. Let's say that I'm wondering whether or not people in the Bronx are older. The population of the Bronx, on the average, is older than the population of Manhattan. Manhattan and Brooklyn have a lot of young people moving into it, especially Brooklyn. That would be interesting, right? To find out if there's a lot of younger people in Brooklyn, the average age is lower than the other boroughs. So let's start with the null hypothesis that the mean of all the boroughs is the same. Mu1, mu2 equals mu2 equals mu3 equals mu4 equals mu5. The average age for people in Brooklyn is the same as the average age for people in Manhattan, is the same for Staten Island, and so on and so forth. So what is that? A categorical variable, borough, 5 possible values, and a numerical variable, age. So I want to compare those averages. Well, let's take a look at what the averages are for starters. I'm going to go to Analyze, Descriptive Statistics, Explore. Okay, you don't necessarily have to do this to do the test, but I want to get a look at the descriptive statistics first. So I'm going to put age into the top of that dependence list. That's going to find the average age. And then down here in factors list, I'm going to say factor it by borough of residence. There it is right up there. Factor it means it break up the averages into those 3 groups. So let's see. I'm going to get statistics is going to be the 95% confidence interval and so on and so forth. It'll give that to me if I want it. Okay, so I'm going to say, okay, I'm going to actually go into plots and also tell it give me a histogram. I don't need a stem leaf plot. It automatically does box plots for you. But right now it's going to make up some graphs for me, find the averages, and so on and so forth for all of these. So let's see what we get. Okay, so here we go. So here there's 1,579 people that responded to this were from the Bronx. From Brooklyn, I got 2,330, and so on and so forth. That's the kind of that's a frequency table. That's what you get with a categorical variable, right? That's the only thing you can really do with categorical variables is get a count of them, right? Bar chart or a count or something like that, so you can compare them. You can't get an average is meaningless. What's the average borough that you live in, right? Doesn't make any sense, right? So that's the number of people that responded in each borough. Okay, and if I go here, I can see that the average age for people living in the Bronx is 47.4. For Brooklyn, it is a little younger, right? 46.71. For Queens, it's 48, a little older. And looks like the geezers are living in Staten Island here, 51.98.
The thing about this is, that's not telling you the people who just moved versus
Right.
the people who've been there.
Only average age. That's all it's telling you. Okay, but that's all remember our null hypothesis was just asking about the average age, right? So it looks like, based on what we can see here, that the average age of people in Staten Island is a bit older, average age for people in Brooklyn is a bit younger, and so on and so forth. But is that statistically significant? Like, in other words, even if the average age were exactly the same in all 5 boroughs, if I did a random survey, I wouldn't get exactly the same number anyway, right? Because there's going to be a little bit of variability. I'd have to be enormously lucky to get exactly the same number, even if they were really the same average, because I'm only sampling a small group. Okay, well, a decent-sized group, but still not the whole population. So now, how do I prove whether or not these means are all the same, my null hypothesis, or that there's some of them that are different, my alternative hypothesis? Okay, that's where analysis of variance comes in. I'm going to say analyze, descriptive statistics, compare means. That's really what I'm doing, is comparing means here. Means of not just 2 people, 2 groups, but 5 groups, each one in the boroughs. Compare means, one-way analysis of variance. Okay, and I'm going to put in my dependence list, I'm going to put the age, which is that first question. Borough of residence goes into the factor, just like before. That's the categories. This is the thing I'm finding the average of. And I'm going to say, okay, it's going to calculate a F statistic, which is the statistic for analysis of variance. And by the way, here's my box plots. Here's the distribution. We can see that the distribution, this end looks pretty normal. It looks like it's skewed to the right because it's kind of weird. It cuts off there. Why do you think it cuts off like that? See if it does it here. It does it on all of them, kind of, right? Suddenly drops off. Why does it do that?
Because they don't ask anyone younger than 18 years old.
Exactly right. There's nobody is surveyed under 18 years old, privacy issues and so on for children, right? But otherwise, it looks fairly normal except for that fact. Okay, how about our box plot? Okay, box plots. These are the mean middle values for each of these. So this one's going to be, we know this one's probably going to be, actually, Manhattan was a bit older even than Richmond, right? I didn't know that. I brushed past it, so I didn't even notice it, right? Which is not that surprising because a lot of people.
That's Manhattan.
Yeah, that's Manhattan I'm pointing at right now. You can actually see it in the scale at the bottom here. It's hard for me to stop it.
Furthest right is Richmond.
Furthest right is Richmond, right? And the lowest one here is Brooklyn, right? So now we have to decide, look at all the variability here though, right? Now we have to decide, can I reject my null hypothesis and say that the means really are different with less than 5% chance of being wrong, right? Alpha equals 0.05. Let's go down to our analysis of variance. If I look at my analysis of variance, it calculates, remember I did that exercise with calculating the sum of squares between the means and sum of squares within the groups. It does that calculation, and it finds that the mean sum of squares is 12,500. The mean within the groups is 301. You divide this into that, and it gives you an F score, which is 41. Usually, when you're dealing with 4 or 5 groups, an F score of 5 or 6 is big. This is 41. It's enormous. So the probability of being wrong, the p-value, the probability of getting this outcome if the means for all the groups are equal, in other words, the null hypothesis is true, is less than 1/10 of 1%. Right? That's why I put that 0 there. Right? So that means I can reject my null hypothesis and accept my alternative hypothesis. My null hypothesis was that all the means are the same. My alternative hypothesis is that at least some of the means are different. Doesn't have to be all of them. Could be just 2 of them. Could be all of them. Could be 2 of them. Could be 3 of them. We don't know yet, right? But we know that at least 2 of them are going to be different. Now that I've done this, found this F-statistic, found that this is true, I can reject my null hypothesis. Now I can go back and do a test to determine which compare each group to the other group. In other words, with 5 groups, you're going to be making 20 comparisons, right? Group 1 to 2, 3, 4, 5. Group 2 to 1, 2, 1, 3, 4, 5. Group 3, and you're going to be doing it like 20 times, right? So we don't want to do that using a t-test because each time we do it, we have 5% chance of being wrong. So we want another test that'll take into account that probability. And those are tests that are called post-hoc tests. I'm going to click on Analyze, Compare Means, One-Way Analysis of Variance. By the way, the problem in the exam is very similar to this, different data set, but we're always doing the same thing. Could be, doesn't matter what the numbers, where the numbers come from. We're dealing with the numbers the same way. And you'll see that there's a different data set in the exam, but you handle it the same way. So now I press on post hoc. Now I can use different kinds of post hoc tests. I'm going to use Bonferroni. Bonferroni and Tukey are probably the two most common. They do them a slightly different way. I won't go into now what the differences in the calculations are, but you can use any of them. You'll usually get the same result. Some are more conservative than others, but for the most part, you usually get a similar result. I'm going to say, okay, go ahead and do it. So now I'm going to get all the same stuff reiterated here. It's going to find the F-score and significance is the same. But now it's going to go through each one of these and compare Bronx to Brooklyn. And my significance, my probability of being wrong if I reject the null hypothesis that the 2 means are the same, is over here under SIG, significance, or p-value, or whichever way you want to determine. So we want a value here that's less than 0.05. So let's see, this first value is 1. Can I reject the null hypothesis? Is Brooklyn and the Bronx, can I say they're different? No. Okay, this one's 0.000. Bronx, Manhattan, can I say there's a difference there?
Yes.
Yes, I can reject null. How about Bronx and Queens? 0.085. Right? Oh, that's pretty small, huh? Yeah, I wish I was a way I could blow this up. It's 0.085.
Yes.
Right, I can't reject that one. 0.085 is bigger than 0.05, right? Got to be less than 0.05. How about Bronx and Richmond? Yes, I can. So I know that the mean for the Bronx and Brooklyn and the mean for Bronx and Richmond are different, right? So how about Brooklyn? If I go down here, if I repeat it again with the Bronx, Brooklyn and Bronx, notice I get the same result at 1.0. Brooklyn and Manhattan, so on and so forth. I can reject the null hypothesis that they're not the same. So you can go through each of these and decide which ones you can say are different and what you can't. See, in this case, it's easier to say that we can't prove that Bronx is different than Brooklyn. And we can't say that Bronx is different than Queens, right? All the others pretty much look like we can, right? Queens, we really can't say is different than any of them, right? Because look at the significance. Oh, I'm sorry, we can. Queens is different than Brooklyn. Yeah, so really, we can't reject the null hypothesis for the Bronx and Brooklyn, or the Bronx and Queens, or for Queens and the Bronx. So that's how we would handle. That's analysis of variance. More than 2 groups. If it had only been 2 groups, if we're only comparing Brooklyn to Queens, we would have used the t-test instead. We would have gone up here to analyze, this compare means, independent samples, t-tests, and we would have chosen the Bronx and Brooklyn. We would have done exactly the same thing. Age, borough of residence, and then see over here, define groups. I would have only put in 2 numbers. I would have put in a number for whatever it was. What was it again? Bronx and Brooklyn. Bronx and Brooklyn were 1 and 2. 1 and 2. And that would do a t-test for us instead of a analysis of variance. So you've got a t-test instead. dirty little secret, if you do an analysis of variance for two groups, right? You could do it for two groups. Nothing, software won't keep you doing it. You'll get exactly the same result as you would if you did a t-test on those two groups. In a sense, if you really look at the math very carefully, you're doing the same thing. Sum of squares and the differences, you're really doing a t-test when you do it for two groups. Right? So don't worry about it. That's neither here nor there. But if you do it for multiple groups, you have no choice. Yeah.
So in the exam, once I check the first column, first row, I say Bronx and Manhattan and Queens and Staten Island are significant.
Yes.
Check the null hypothesis.
For those.
Stop there, right?
For those, yeah. For those particular boroughs.
I have to say for all the others as well, or I can stop there?
Well, no, actually, if you just say Bronx, let's see.
That already shows that
yeah.
null hypothesis.
Yeah, it really does everything twice. You're right about that, right? But Bronx and Manhattan, Bronx and Richmond, right? But are there any others? Well, there's Brooklyn and Manhattan are different too, right?
Yeah, but if
as long as you catch all the differences.
Oh, we have to catch all the differences?
Yeah, all the differences, right? For instance, this first box, right up here, this one shows you that you can reject the null hypothesis for Bronx and Manhattan, but also Bronx and Richmond. But you have to go down here to reject for Brooklyn and Manhattan, and Brooklyn and, well, you already got Brooklyn, Brooklyn and Queens, right? And down here, if I go down here, I got Manhattan and Bronx, which I have already, Manhattan and Brooklyn, which I have already, Manhattan and Queens, which I don't have, I don't think yet.
But the null hypothesis are that they are all equal.
Right, and the alternative.
If I show a few that are not equal, that means that hypothesis is not valid.
Yeah, but you might also be interested in which one, all of them. You know, in other words, your null hypothesis, you've rejected your null hypothesis. Now you're doing a post-hoc test to figure out which ones are really different. Some are, some aren't. For you, when you reject your null hypothesis, doesn't mean all the means are different. It only means that you've proven that some of the means are different. So this table, a lot of the time, you may not be interested in all the other boroughs. You may only be interested in a few of the boroughs, right? So, but this table gives you everything. In fact, it gives it to you twice. Repeat, because if it's comparing Manhattan and Queens, when the box on the left says Queens, it's also going to compare Manhattan again. But yeah, actually, if you wrote down every group that's different here, it would probably be about 6 of them that are different. Brooklyn, Manhattan, whatever it comes out to. That's analysis of variance. That's what you would be doing. Okay. They may on the test may ask you, well, what are the assumptions for analysis of variance? Right? Homoscedasticity. Right? Remember that word? Yeah, that word came up. The variability is the same. But now don't have to be exactly the same, but they're pretty much the same. That's one of the assumptions. Random independent samples. So if that question comes up in the test and you don't remember, you can go to the textbook, or you can go to the PowerPoint. Has a slide, tells you what the assumptions are. Right? So that's what you can expect kind of on the test. Won't be the same data, but it'll be questions like that and an analysis like that. I think on the test it's 4 groups, not 5 groups, something like that. Some other kind of much simpler database. Right? This is it's a complicated database. This is 8,000 people responded to this question, right? You lose track of that because SPSS handles it so quickly. It's such a simple job in SPSS. Okay, so I'm going to go on to another one now. Okay.
Will we be tested on 2 kids?
I'm sorry?
2 kids.
Tukey? You mean the other post-hoc test? I think it tells you which post-hoc test to use.
Okay.
In other words, should I use Bonferroni, LSD, Tukey? Which of the tests should you use? I'm not going to leave that up to you. I'll tell you which one to use.
But are we good? In the test, do we have to use the test, execute the test?
Oh, okay. That's good. Let's give it a try. Analyze, compare means, analysis of variance, and when you go into post-hoc, you tell it which one you want to use. So I checked off Bonferroni. I could check off both, do both, if I wanted to. I'm going to do that just so we can see the result. So you would normally only use one of them.
So how do you interpret it? There's 2 columns there. So all the groups in one column are equal, and the other they are different from the other columns.
I'm not sure. I'm
Two
not.
kids.
Yes.
Go down to 2 kids.
I got it here. Okay. The thing we're really interested in here is the significance.
Oh, okay.
Right?
Same thing.
Right, exact. And if you look there, it's let's see if you look, you get the same result. We miss Queens by a little less. Remember, the other one was 0.085. This one's closer. It's less conservative test, right? So it came a little closer to being able to say that they're different means. But it does say Bronx and Manhattan. You know, you can say they're different. Bronx and Richmond are different. Brooklyn and Manhattan, they're different, and so on. So we got pretty much the same result. Down here is the results for Bonferroni. Up here are the results using that method, using a different method.
What about the other table at the right at the bottom? The groupings.
Oh, well, these are the averages, I believe. Isn't that what this is? Subset alpha, borough residents. This is the number of people that responded. And this looks like the average ages. Right? 2, 10, 10. That's a good question. Brooklyn and the Bronx. Brooklyn, Bronx. 2. Subset for alpha equals 0.05. Maybe this is a summary of the ones that are different, the ones that you successfully rejected the null hypothesis at that level. That's probably what it is. In other words, if you look at these, if you look at the ones that are highlighted here, Brooklyn and the Bronx, Brooklyn and the Bronx, 0.82 significance, 0.12. No, those are the ones that are not different. Oh, maybe these are the only ones that are not different, that you can't reject the null hypothesis for, right? Because you see the significance down there is all bigger than 0.05. And they highlight Brooklyn and the Bronx, which we know Brooklyn and the Bronx were not a significant difference. So that looks like it's highlighting the groups that you could not say that the means with that level of certainty, 0.05, alpha equals 0.05, that you could not reject the null hypothesis for. In other words, yeah, that's what that looks like, yeah. And it happens to also give you the means, right? Kind of convenient.
This table is those that you cannot reject.
Exactly. That's what it looks like, right? Yep. Okay. All right. All right. So now let's take a look at, let's go move on to correlation and regression. So I'm going to open up a data set from correlation and regression. You know, I'm going to go purposely back to Firefox and to our Blackboard site so that I come up with a file that you guys have. Come on, load. Okay, good. Let's see. Actually, yeah, I don't have two numerical variables in there. Let's go to weekly sessions. Let's pick out an interesting database. Oh, violent crime. Oops, that's an Excel file. I don't want that one. Do I have a? Here we go. We got the SAV equivalent of it. This is an SPSS file. Title of it is Violent Crime, and it has a number of different parameters that examine the levels of crime for different communities, I think. Well, let's see it for sure when it opens up.
In different cities.
Is it cities? Yeah. Yeah, different cities and Washington, D.C., I believe it is. This is from a while. Oh, states? Okay. Okay, there we go. Yep. There we go. Okay, let's take a look at what we have here. I guess this is the number of violent crimes during a certain period of time. This is the murder rate per 100,000, I guess. This is the poverty rate, percentage of households that are below the poverty rate, level. This is the percentage of people graduating high school. This is the percentage of people that have taken college courses, the percentage of single-parent homes, the unemployment rate, and so on, and an index for how much of a metropolitan area it is, how densely populated it is. Okay, so these are all numerical variables. They're all numbers, right? So let's say I'm interested in investigating whether or not the murder rate has something to do with the poverty rate. Okay, two numerical variables. Okay, what I'm looking for there is a correlation. As the poverty rate goes up, does the murder rate go up as well? First thing I might be interested in doing is just looking at it visually to see if there appears to be an association. So I'm going to go over here to Analyze. I'm going to go to, where is it? My version of SPSS has this really annoying property that it doesn't give me all the menus when I'm in the data window. I have to switch to the output window. Hopefully yours doesn't do that.
So you're going to analyze?
Yeah, I'm going to graphs.
Right.
Graphs, legacy dialogues, and I'm going to go down to scatter dot. Scatter dot is just like an XY plot. Okay, simple scatter dot, define. Now I'm going to, on the x-axis, I'm going to put the poverty rate. Is that what I said I was going to? Yeah, I was going to use poverty rate. And on the y-axis, I'm going to put the murder rate. I'm going to click OK. Okay. It's kind of hard to see because all these places are down here, and this place up there gives me a problem, right? Right. You want to know what that place is? That was that year they had an extraordinarily high murder rate in Washington, D.C. It's an outlier, right? Something was going on where there was a big drug, there was a crack epidemic, there was something going on in Washington, D.C. that resulted in a lot of murders that are really out of line with the rest of the country. And it's also not a state, it's a city, right? So small population, same number of murders, is going to look like a much higher rate. So I'm thinking, let me go back to my data file. And I'm going to remove Washington, D.C., just to make it easier for us to work with this thing. Okay, let's see where it is. Yeah, see Washington here. Oh, I'm sorry. Is that the beginning? Oh, there you go. That's true. Yeah, look at the violent crime rate and the murder rate compared to all the others. So I'm going to just say that that's an outlier. I'm going to clear it. I'm going to remove it. I clicked on. I opened. I got to Window, and I chose the data window. Okay, go here, Window, and I can go to Output, or I can go to Window and go back to the data window. Listen, I do the same thing. I got 90 windows up in here, so don't feel bad if you went to the wrong window. Okay, so now, okay, I'm gonna again now I'm gonna go to my output window here. Graphs, legacy dialogues, scatter plot. Yep, and you'll see the result of that when I do it again.
District of Columbia.
Yep. Yeah. So there you go. Now it looks like an association there. You can see as the poverty rate goes up, it appears that the murder rate also goes up. I'm going to double click on this because it'll bring up an editor in the window. One of the things I can do is tell it to make a best fit line to fit this data. Okay, and it should put it right in for us. I did get the right one. Yeah, I did get the right one. Okay, there we go. There it goes. And there's a little formula that comes up there. It's a little premature right now, and it's the thing over here, R squared. It's a little premature right now, but it comes up. So this is the best fit. This describes, it tries to equalize the square of the differences between each of these values below and above. Okay, and had we had Washington in here, it would have been way up here, made the slant that is very dramatic and really messed things up a bit. So now, it's not perfect, right? So if it were perfect, every one of these dots would be on a straight line. That's a perfect correlation. If I did this for BMI, and I put BMI versus height or weight or something like that, it would be almost a straight line because it's a formula that's based on that, right? So a perfect correlation would be everything on a straight line. We don't often find that, but a lot of times we find good, useful correlations. So how good is this correlation? Okay, and the way we can do that is we can go here And we can say to analyze. I'm going to close that window. Okay, that's okay. I'm going to say analyze, and we have a function correlate. This is bivariate correlation because there's two variables, bivariate, and I'm going to move the two variables I'm working with in here, violent crime rate and the murder rate. Okay, I'm going to click OK. And notice Pearson was clicked off there. This is a Pearson's correlation. Okay, the value of Pearson's correlation, it's called R. The value of Pearson's correlation is 0.712. A correlation of 0 means that there's no association between the two variables. In other words, for instance, the price of eggs by month versus the I come up with the number of astronauts on the space shuttle, on the space station. No correlation between the two. That would have a correlation of 0, right? So, but if you have a correlation of 1, it's a perfect correlation. Everything is on the same line. It's perfectly correlated. As one goes up, the other one goes up in an absolutely predictable manner. Okay. Now the fact is that this is a 0.712. That's closer to 1 than to 0. So I would call this a strong correlation, right? There's a strong association between the poverty rate and the murder rate. A violent crime. Did I make a mistake and put the wrong one? Yeah, what are you going to do? Okay, let's stick with this. Let's stick with this one now that I did it. Okay, I got a nice strong association.
Sure, I was like, wait,
Let's. Yeah, I got a good result. Yeah.
I did that one.
Okay. Yeah. For instance, if the poverty rate is 10%, we would expect that the murder rate is going to be about 3.7 or 8 per 100,000, right? And murder rate on here, right? So I did the correlate. Unfortunately, I did the. Let me go back and do it again. Analyze. It's easy enough to do since this is doing all the work, right? Okay. Yeah. Let me get violent crime out of there and do murder and do poverty. Okay. Okay. Actually, it's not as good a but I mean that you would think kind of murder and violent crime would go together. Violent crime and murder basically the same thing, right? So, but it's still not a bad correlation. It's a decent correlation. 0 is not a good correlation, right? Okay. So now the
poverty and unemployment.
we can try all of these. As a matter of fact, each one of them. Now the thing I want to point out here is that's a positive number, 0.427.
Yeah.
It's a fairly good association correlation, and it's 0.427, positive number. What do you think a positive number means when on the Pearson's correlation, that R value? It means it slopes up. As 1 increases, unemployment increases, the murder rate increases.
It's not that strong.
What if not quite as strong as the other one was, but yeah, it's still okay though. What and it's significant. See the significance there, 0.002, right? It's statistically significant. What about if I told you that was a negative 0.427? What would that mean? The slope would go down. In other words, as the poverty rate went up, the murder rate went down. I don't know how that would happen. Can't afford to buy guns, I guess. Maybe that's whatever, right? You wouldn't expect that to happen, right? So the murder rate went down, right? So, but that's obviously that didn't happen here. In the real data, it went the other way around, right? So at any rate, let's see. So now there always seems to be money for guns, right? In this country. You can run out of food. We ain't going to run out of guns anytime soon. Guns remind me of golf. I hate golf. I hate golf, right? It's the worst game in the world. There's somebody who wrote a book a long time ago that described golf as a good walk spoiled, right? It's really a frustrating game, right? So, but one of the things when I was golfing is I noticed I was hitting a lot of them into the woods, and half the time I couldn't find them anymore. So, and a lot of other people were hitting them into the woods. So I'm thinking about they're making billions of golf balls every year, new golf balls. Where did the old golf balls go? You would think they'd be piling up somewhere, right? Same thing with guns. They keep making more and more guns, right? I've never seen anybody throw a gun away. They must be somewhere in this country where there's a billion guns sitting somewhere in a shack or something like that. But yes, at any rate, let me get back on the point here. So at any rate, I'm easily distracted. So that's our correlation. But now let's say we want to quantify that, right? We want a formula that will help us predict if the poverty rate is such and such, what can we expect the murder rate to be? Okay, so I'm going to go into here. I'm going to go to analyze, and that is where we use regression. In this case, it's linear regression. We're going to assume it's a straight line relationship like the one we drew. Now, when I do that, I have to choose a dependent variable and an independent variable. The independent variable is the predictor. The dependent variable is the one that is determined by the predictor variable. So in our case, the independent variable is poverty rate. And the dependent variable, or in other words, the predicted variable, is the murder rate. So I'm going to go ahead and say OK. And it's going to do a calculation for me. And it produces a number of tables. The first table it produces is a model summary, including it does that Pearson's R value calculation. Again, there it is, 0.427, right? It also calculates R squared. And R squared comes up to, which is 0.427 times 0.427, comes up to 0.182, right? That's R squared. Interesting detail about R squared. R squared represents the amount of the variability between poverty level and murder rate that's explained by poverty level. What percentage of the change in the murder rate is explained by the change in the poverty level? The higher the R value is, the better the correlation is, the more of the variability, the change in the variability, the amount of how much it varies from what we expect for the output variable, the dependent variable, the more of it that's determined by that independent variable. 18% of the variability in the murder rate can be predicted or is predicted by the poverty rate. What does that tell you? That tells you there's a lot of other things that influence the murder rate besides even though poverty rate does seem to influence it, there are 80% of the variability is due to other things. In fact, if you ever take another course, you might get involved in multiple regression. And in multiple regression, they'll create formulas that will include all of the other variables, the poverty level, the percentage of single mothers, the urbanization, all these other variables. They put that all into a formula, and it would be a better predictor of the murder rate because you'd be involving more factors. So instead of just what we're about to do is going to create a formula. Instead of a simple formula, it's going to be a more complex formula. So I'm going to go down here, and again, it calculates the probability of this being by chance, and it's small. Okay, down in this last box, we have something called coefficients. Okay, now, in order to explain that, a straight line can be explained by, I don't think I have my head. Yes, I do. Yeah, let's plug this in. Okay. Where is it? Well, I know it plugs in here somewhere. Oh, this is in the way. That's what the problem is. Okay.
Coefficient fall under B, correct?
Yeah, that's the y called the y-intercept. I'm gonna show you that right now. Okay, there's not enough stuff on my desk here, so I'm gonna make it even worse. Okay. Okay. So let me see if I can't get these coefficients so that they're visible here. Okay, here we go. This is good. Okay, so you probably remember that we looked at this chart. We made this graph, and it looks something like this. Dot, 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 dot. Where am I? And we drew a best fit line, like so. This is the poverty rate. This is the murder rate. Okay, so now I want to describe that line. And from our old algebra days, y is equal to mx plus b, right? I think most statistics books show it as y is equal to ax plus b or something like that, or bx plus b, bx plus a, right? Okay, but it's really the same thing. The number in front of the x is the slope of the line, and the other number is the y-intercept. In other words, when x is equal to 0, this is where it crosses, that y is equal to that number. In other words, that's where it crosses the y-axis, right? But we could write a formula that describes this line exactly. So if we look at our chart that came out of our, oops, let me get it to scroll up. If we look at this chart of coefficients, we see that poverty has a coefficient of 0.365. That's the slope of this line. Okay, so in other words, y is equal to 0.365 times x, which is poverty, plus the y-intercept. And the y-intercept is this other number, 0.432, the constant, right, 0.432. Okay, and in fact, I can actually substitute for y and x. I can just call them the murder rate is equal to 0.365 times the poverty rate plus 0.432. Okay, so now what does that mean? Let me think about this now. So if the poverty rate is, let's see, 0.365, okay. So if the poverty rate is 10%, right? Okay, equals, I wonder if I got that formula right. Standard error. That number seems a little odd to me. No. Let me see if I can't find it back here. Okay, murder rate's 4. So the poverty rate of 10% should be, oh, okay, it's going to work. Okay, good. So in other words, if the poverty rate is 10%, right? That's going to be a number 10, right? And we're going to multiply it by 0.365, right? That's going to be equal to 3.65 plus 0.432. Okay, what's that going to be equal to? It's going to be equal to roughly 4. So we would expect the murder rate to be equal to about 4. Okay, so if I go back to my graph, okay, the poverty rate is not, they give the percentage as a number, percentage, not as a decimal place. That's why I was getting a little mixed up there, because I was thinking it was going to be 0.10, but it's actually 10. So the poverty rate is 10%. Then if I go up here, the murder rate that line represents is just a tiny bit under 4, right? But if I look at any of these individual states, almost none of them are right on the line. This one happens to be right on the line, right? A lot of these are not right on the line. The difference between the actual number and what the line predicts is called a residual, right? So in this case, let me find one that's close to 10. Let me find one that is like, let's see. I'm running out of time here. See this one right here, whatever state that is? That one, the formula predicts the murder rate for that one perfectly. For these others, it doesn't predict it perfectly. And the difference between what the line predicts, which is, in this case, it would be 4.2, when it's actually 6.6 or something like that, that difference is called the residual. Well, what?
Above the line.
The residual is positive. If you're below the line,
so it underestimates.
Right, exactly. The line underestimates all the ones above the line, overestimates all the ones below the line. So why is this of any use to us at all? Well, because it helps us understand, number one, the effect of an increasing poverty level in general on the murder rate. Remember that slope we were looking at? That predicts for every percent increase in poverty rate, there's going to be approximately 0.4 murders per year more, per 100,000, per 10,000, right? It helps us understand the magnitude of the effect. The other thing it helps us do is if it's a good correlation, we might be able to use it predictively. In other words, if we know that the poverty rate, we don't have statistics for the poverty rate in state X, right? But we know if we don't know the murder rate in state X, but we know the poverty rate, we can use that poverty rate in this formula to estimate what we think the murder rate is likely to be. Okay? So you can use it to that effect. And it's important because a lot of the studies that we're going to do are going to involve numerical variables, and we're looking for these associations. And it also puts into perspective for us the magnitude of the effect. In other words, if I see that the slope for the poverty rate and murder rate is 0.365, but I see that the percentage of single mother families is 0.825, the slope is much greater. I might say to myself, I want to put my public health money and funding into supporting single mother families rather than specifically targeting it to improving the poverty rate. You know what I'm driving at? Right? That slope of that line tells us how much changing the poverty rate or changing one of the other variables will affect the murder rate in this case. I'm not sure I picked necessarily the best variables here, but for instance, on the test, you could do exactly the same thing. You could calculate the correlation, see if it's a good correlation or not a good correlation. You can then also calculate R squared and get some feedback on how much of the variability in the outcome variable is due to the predictor variable. And you can create this line and actually use it to predict a value. Like for instance, well, what if this is equal to 10? What would you expect the dependent variable to be equal to? So very similar to what we just did here. I'm going to go over this. On Saturday, I'm going to go back again, do a little bit of the earlier stuff, just to kind of cement it in. But I'll go over this a little bit as well. So if you do your first effort after this, if you take your second shot afterwards, maybe it'll fill in some questions for you as you do it. Okay. So good luck on the test, right? I think it'll be a good learning exercise because I think I really like the way the homework's worked out. I saw some people, I mentioned this before probably, I saw some people who take a homework and do it like 6 times. And each time they did it a little bit better, right? And then eventually they got pretty close to 100. Maybe not always 100, but they got pretty close to 100. And it was like, I could see them learning. I could see them, oh, now I figured this question out. Now I figured this question out. So I like that. I like doing it this way. So hopefully the exam, in addition to being a test, they make me put grades on. If I don't have to put grades on, I wouldn't do it. They put a gun to my head. You got to grade everybody. But they make me grade. So I need this. We need exams. We don't want to have grades and so on and so forth. So I like the idea of making an exam also a learning process also.
Is that why we're here?
Yeah, I hope so.
Not to take a test.
Yeah, but you want to know something? Yeah, that's true. But there's so much emphasis on grades now. Really, it's really